School tells us that one half means half a pizza, half a cake, half a chocolate bar, and for a while that explanation works. Until mathematics start asking questions that pizza can no longer answer. What is half of 5 meters? What is half of an angle? What is half of velocity? Half of an electric field? Half of gravity? And suddenly there is no pizza anymore. And yet, the fractions still work perfectly. So, maybe fractions were never really about cutting objects into pieces. Maybe this was just the first language we learned. Think about 5. If I write 5, nothing moves, nothing changes. It's simply a location on a number line. Now imagine I write 5 times half. Most people imagine the number itself shrinking, as if someone grabbed the 5 and squeezed it smaller. But that is not what mathematics is doing. Imagine you standing on an infinitely long road. Every number is painted onto the ground. 0, 1, 2, 3, 4, 5, 6, 10, 20, 100. Now imagine reality begins to compress. Not on the numbers, on the road. Every meter becomes half as long. The painting never moved, the labels never changed, only the space between them did. 5 doesn't become smaller because 5 changed. 5 becomes smaller because the universe around 5 changed. That sounds like science fiction, but mathematically, that is exactly what is happening. The fraction isn't attacking the number, it's quietly rewriting the geometry underneath it. And once you realize that, fractions stop looking like arithmetic and start looking like physics. Here's another way to say it. Imagine your city painted on a giant paper map. Now, place the map into a photocopier. Reduce it to like 50%. Did any building disappear? No. Did roads vanish? No. Everything still exists, only the scale changed. That is multiplication by 1/2. Fractions are just scales machines. Think about every time you used to use your phone camera. When you pinch inward, nothing inside the real world becomes smaller. The tree outside your window doesn't shrink, the buildings across the street doesn't collapse. Your camera simply changes how much space everything occupies on the screen. Mathematically, that is exactly what multiplying by a fraction does. It changes the scale of representation, not the existence of the object. Now, imagine your screen is actually the number line. 0 stays where it is, but every other number begins to slide towards it. 2 moves closer, 4 moves closer, 8 moves closer, 16. Every distance contracts by the exact same ratio. Notice something beautiful. The pattern never breaks. The spacing changes, but the relationship stayed perfectly intact. That is called similarity transformation. Geometry recognizes the world as exactly the same, just viewed at another scale. That is why fractions preserve structure. Triangles remain triangles, circles remain circles, and functions keep the shape. Reality doesn't become distorted, it becomes smaller. That is a profoundly different idea from what most of us learned in school. Now imagine standing in a room. Now imagine every wall slowly moves towards you. The furniture gets closer, the ceiling slower, and the floor raises. The room isn't disappearing, the coordinate system is shrinking. So that is what multiplication by 1/2 feels like if you could actually experience it. Now comes the part that actually confuses almost everyone. If 1 meter is smaller than 1, why does dividing by it create a larger answer? Well, at first glance, this feels impossible. Our intuition says smaller things should produce smaller results, and larger things should produce larger results. So, where did the extra numbers come from? Let's stop thinking about arithmetic. Instead, imagine you're filling a bookshelf. You have 8 meters of shelf space. If each book is 1 meter wide, you can actually fit 8 books. Simple. Now imagine every book suddenly becomes half as wide. Did the shelf become longer? No. Did it create more wood? No. You simply change the size of what you're counting. Now, 16 books can actually fit in. Nothing magical happened. You change the measuring unit. Division has been secretly asking this question all along. Not what is 8 divided by 1/2, but how many half-sized units can actually fit inside 8? Now, the answer feels obvious. Of course, it is 16. A half-sized thing fits twice as many times. Now, let's push this further. How many quarter meter rulers fit inside 1 meter? 4. How many 10-meter rulers fit inside 1 meter? 10. How many 1,000 meters rulers fit? 1,000. Notice the pattern. As the measuring units become smaller, the answer becomes larger. Not because reality grows, but because you're counting with finer resolution. And that is what fractions really are. They are resolutions. Just like increasing the pixel in a photograph reveals more detailed. Using smaller fractions reveals more measurements. Division isn't creating numbers. It's revealing subdivision that will always there. And once you understand that, dividing by fractions stops being a strange trick. It becomes one of the most natural ideas in mathematics. So far, we've been talking about numbers. But what if numbers aren't the real thing being transformed? What if something much deeper is changing? Imagine a giant rubber sheet stretching endlessly in every direction. Now, paint a number line across it. 0, 1, 2, 3, 4, 5. Every number is painted exactly 1 unit apart. Everything looks perfectly ordinary. Now, imagine grabbing both ends of that rubber sheet. Slowly, we begin pulling. The sheet stretches. Every painted number moves far away from its neighbor. 1 or 2 are no longer 1 centimeter apart. They are 2 centimeters. Then 4, then 10. Notice something fascinating. These numbers themselves haven't changed. 1 is still 1, 5 is still 5, and 10 is still 10. Only the space between them changed. And that's the first strange realization. Number doesn't really move through space. Space moves around the numbers. Now, reverse the process. Instead of stretching the sheet, you compress it. Numbers lie closer together. The entire universe becomes more compact. Again, nothing disappeared. Nothing was destroyed. The geometry underneath everything simply changed. This is the hidden machine that fractions have been operating all along. When you multiply by 1/2, you're not shrinking numbers. You're compressing the space they inhabit. When you divide it by 1/2, you're stretching that sheet back out. Think about a printed photograph. You can enlarge it, you can shrink it, you can project it onto a wall, print it onto a postage stamp. Every relationship inside that image remains exactly like the same. Mathematics call this similarity transformation. It preserves shape while changing scale. And that is why fractions are so powerful. They don't destroy information, they recognize it. Now let's go even deeper. Suppose someone hands you a true map. One is the size of a postcard and the other covers an entire wall. Which one is more accurate? Well, at first, you probably say the giant one. But look closer. Every road connects to the same city. Every river flows the same path, and every mountain sits on exactly the same location. One map isn't more real. One simply uses a different scale. Fractions work exactly like the scale printed in the corner of every map. The map labeled 1/100,000 doesn't change the Earth. It changes how Earth's distances are represented. That tiny ratio quietly stretches or compresses an entire world into a paper. And that is exactly what fraction does. Not just on map, on number lines, on graphs, inside equations, even inside geometry itself. The fraction isn't touching the object. It's touching the ruler you're using to describe it. And once you see that, fractions stop looking like arithmetic and start looking like hidden architecture behind measurement itself. At this point, you might be thinking, this is interesting, but this isn't just mathematics. Actually, this is where things become surprising. Because the language of physics is almost entirely built from fractions. Take velocity, meter per second divided by time. Acceleration, meter per second. Force, mass times acceleration. Density, mass per volume. Pressure, volume per area. Power, energy per second. Frequency, cycles per second. Everything you look, fractions. Why? Why does nature seem obsessed with dividing one thing by another? The answer is beautifully simple. Because physics isn't just interested in things. It is interested in relationships. Imagine driving two different cars. Both travel 100 kilometers. Did they perform equally? Not necessarily. One took 1 hour and the other took 10 hours. The distance tells only half the story. The relationship between distance and time tells the real story. That is what velocity measured. Not how far, but how far for every second that passes. Now imagine two bugs. Each weigh 10 kg. They seem identical until you discover that one is the size of a suitcase and the other is the size of a marble. Same mass, completely different density. Again, the important quality isn't just object itself, it is the relationship between two measurements. Fractions reveal those relationships. They are comparison machine. They ask compared to what? That's why physicists constantly divide quantities. They are uncovering how one aspect of reality changes relative to another. In fact, some of the most fundamental constants in the universe are themselves ratios. Even the slope of a graph, something as simple as a line, is a fraction. Rise, overrun. Without fractions, graph couldn't describe motion. Without ratio, equation couldn't describe nature. Without scaling, physics couldn't describe the universe. Fractions aren't just a chapter in mathematics, they are one of the operating principles of reality. Here's the strange part. Long before you ever learned fraction in school, your brain was already using them every second of your life. Look down on a railway track. The rails are perfectly parallel. They never meet. You know that you could measure them with a ruler. Yet, they appear to converge onto a single point on the horizon. Your eyes isn't broken. Your brain isn't making a mistake. It's performing a scaling transformation. The farther something is from you, the smaller its image becomes. Twice as far away, roughly half the apparent size. 10 times farther away, only a tiny fraction of the size. Think about a friend walking away from you. They don't actually shrink. Their height stayed the same, their body didn't compress, their atom didn't become smaller. Yet, they occupy less and less space on your retina. Your visual system is constantly multiplying reality by fractions. Not because the world changes, but because your coordinate system changes. Every camera works this way. Light from an enormous landscape is compressed into a tiny sensor. A mountain hundreds of meters tall becomes a few millimeters of light. An entire city fits inside your phone. How? Fractions. Perspective is nothing more than continuous scaling. Object farther receive smaller scaling factors, and object nearby receive larger ones. Computer graphics uses this exact principle. When a video game renders a distant building, it doesn't actually rebuild the building. It applies a scaling transformation. Every vertex moves according to the perspective equation built from ratios. The same mathematics behind a simple fraction is also behind every realistic 3D you could ever explode. And suddenly, fractions aren't just living in textbooks anymore. They are inside your camera, inside your eye, and inside every movie and every video game. Every printing that creates the illusion of depth. And you spent your entire life looking at fractional transformation without even realizing it. Because fractions were never just about cutting pieces into slices. They've been quietly shaping the way you experience reality itself. Until now, we've been looking at fractions through mathematics, through physics, through the way we measure the world. But what if I told you nature itself seems to have a favorite mathematical trick? Not addition, not subtraction, not even multiplication. Scaling. Imagine you're flying high above a coastline, from thousands of meters in the air. It looks smooth, simple, almost elegant. But as you descend, something strange begins to happen. The closer you get, the more details appears. Tiny curves become jagged edges. This jagged edge split into even smaller curves. Those curves split again and again. No matter how much you zoom in, new structures keep appearing. It is as if the coastline refuses to become simple. Now imagine taking a tiny section of that coastline and enlarge it. Surprisingly, it begins to resemble the entire coastline. Not perfectly, but closely enough that your brain recognizes the pattern. You're looking at one of nature's deepest ideas. Self-similarity. Small pieces resemble the whole. How can that happen? Because nature keeps repeating the same shape at different scales. And every time the scale changes, fractions are involved. Imagine shrinking a branch of a tree to half its size. Then grow two smaller branches from it. Then shrinking those branches again. Then repeating the process thousands of times. Eventually, you don't just have lines anymore. You have a tree. Now look at your lungs. The airway divides again and again and again. Each new branch is smaller than the rest. Blood vessels spread through your body the same way. Lightning flows across the sky using similar patterns, and river systems divide into streams. Streams divide into creeks. Even the neurons inside your brain from branching networks repeat the similar structure across different scales. Nature rarely builds something completely new. Instead, it takes an existing pattern, shrink it, copy it, and repeat it over and over and over again. This idea became so important that mathematicians gave it the name, a fractal, a shape created by repeating scaling. But do you notice what makes this extraordinary? Fractions aren't decorating nature, they are generating it. The incredible complexity we see in forests, mountains, clouds, and coastlines can emerge from one simple instruction repeated endlessly. Make the next fraction just a little smaller. Sometimes one half, sometimes one third, sometimes another ratio entirely. Complexity born from scaling. So the next time you look at a tree, remember, you're not just looking at woods and leaves. You're looking at thousands of fractional transformations frozen into a single object. At this point, you probably notice something. Fractions keep appearing everywhere, not because mathematicians enjoy making life complicated, but because the universe keeps asking the same question. How does this change relative to something else? Let's leave mathematics for a moment. Imagine a guitar string. When you plug it, it vibrates at a certain frequency. Now, press your finger exactly halfway along the string. The vibration length becomes half as long. Something fascinating happens. The sound doesn't become half as high, it becomes an octave high. By changing the scale of the string, you transform the sound itself. Musicians have been using fractions for centuries whether they think about them that way or not. Now, think about photography. A photographer steps backward. The people in the picture appear smaller. That picture becomes larger. Perspective changes not because reality changed, but because the scaling relationship changed. Architects use scaling before a single brick is laid. Engineers use scaling before a machine is ever built. Designers create miniature prototypes knowing that the same relationship will hold when the object becomes enormous. Even the internet relies on scaling. Every image on your screen, whether it's a tiny icon or a massive billboard, is constantly being resized. Your phone smoothly scales map as you zoom. Video games scale entire world 60 times every second. Every animation you watched, every movie you enjoyed, every digital planet you've explored depends on mathematics of scaling. Even this video, every object you're seeing right now, every equation, every animation have been continuously scaled, transformed, enlarged, and reduced before reaching your screen. Fractions are quietly working behind the scene, not demanding attention, just making modern technology possible. The strange part is we rarely notice them because scaling feels natural. We've lived with it for so long our brain treats it as ordinary. But once you begin looking for it, you realize something astonishing. Fractions aren't confined to mathematics classrooms. They've woven into music, engineering, architecture, computer graphics, medicine, astronomy, and perhaps into the very fabric how reality organizes itself. Now, let's return to the question we started with. What is 1/2? For most of our lives, the answer seems obvious. Half a pizza, half a cake, half a chocolate bar, half of something. But after everything we've explored, that answer suddenly feels too small. Because 1/2 isn't merely a piece, it is an instruction. An instruction that tells space how to reshape itself. Now, imagine the universe handing you a command. Not remove half, not destroy half. Instead, take every distance, every moment, every coordinate and multiply it by 1/2. Instantly, the world becomes smaller. Every mountain, every planet, every atom, every step you take, every graph, every photograph, every mathematical object. Not because everything disappeared, but because the geometry underneath everything changed. That is what 1/2 has been saying all along. It is not describing an object, it is describing a transformation, and that is why dividing by 1/2 feels so strange. You're not creating extra numbers, you're undoing the transformations, you're stretching the compressed world back outward. The numbers were never hidden. Perhaps that is the biggest lesson hidden inside fractions. Mathematics isn't always about counting things. Sometimes it's about changing the world you're counting in. The number stays exactly where they are, but your perspective changes. Your ruler, your coordinate system, your notion of distance all quietly shift beneath your feet. And once that happens, the impossible suddenly becomes obvious. A number smaller than 1 can make another number bigger. Not because mathematics broke its own rule, but because we finally understood what the rule was saying all along. So, why does fractions stretch reality? Because fractions aren't really small numbers. They are scaling operators. They don't simply tell us how much of something exists. They tell us how the entire space around things to be measured. And once you see a fraction that way, you start noticing them everywhere. In the branches of a tree, in the rhythm of music, in the perspective of painting, in the equation of physics, and in the graphics powering your favorite video game. And even in the way your own eye transforms the world every time you look into the distance. The humble fraction, one of the first ideas we learned as children, turned out to be one of the most deepest ideas in mathematics. Not because it is complicated, but because it is everywhere. And yet, fractions are only one kind of transformation. There is another number, one that doesn't stretch space or compresses it. A number so unusual that mathematicians have spent centuries arguing about how to handle it. A number that can make an equation collapse, break symmetry, and forces us to ask what numbers really are. 0. That only number seems capable of breaking mathematics itself. And that is exactly where we're going next. If you like this, make sure you like and subscribe for more, and I hope to see you next time.